So, hello all. We will wait for a few moments. Let others join here, and then we will start in a couple of minutes. All right. Good evening, good morning, good afternoon from wherever you are. So, uh, this is Kumar Hemant, and I will be co-hosting today homework session. And about me, so I hold a bachelor in physics and master in mathematics and computing, and have worked earlier with IBM Research, Samsung, and nowadays I'm trying to do entrepreneurship at the same time learning quantum. So if you have any questions, you can pretty much start asking here, and I will be happy to answer. At the same time, let me share my screen and take questions of homework one by one.
Hey everyone, it's Katie on the CubeIQ admin side. I think everyone should have ability to unmute themselves too if you prefer to ask your question through the mic than chatting.
Yes, it's perfectly okay. You can unmute yourself, or even you feel shy, you can pretty much type your questions which you would like to ask here in the chat box.
Yeah, I have a question from the last week. Like, what exactly is electron spin?
Right. So electron spin is, so there are kind of two kinds of a spin. One is where it is rotating in the around nucleus, and one is its axial spin, which is rotation. So so GS experiment is, or SG experiment, Gerlach experiment actually proved that electron has got its own spin around its own axis, and that is where the spin is pretty much just like an Earth rotates on its axis, which is of course similar kind of.
Excuse me, could you talk a little bit about around the confinement topic, what it is exactly? Confinement.
Yeah. So say again what you want to know. Who is this? Alberto. Yes. Please.
So if you could help me with the concept of confinement, its function and nature.
Sorry, can you hear me?
There might be a mic problem.
Oh, okay. Am I audible now? Okay, I was on mute,
Gotcha.
perhaps.
Yeah.
Yeah. Yeah, so any questions from, okay, so question number 7 and 8. All right, so question number 7, let's look at. So question number 7 and 8 is related to some conditions are given here. Let me read it for you. Now consider an experiment which measures an observable represented by the operator O. This could be position, momentum, energy, spin, etc. And this operator O has 4 eigenvalues, and this alpha, beta, gamma, and delta. This corresponds to 4 eigenstates. Okay, so A, B, C, and D. This is kind of Ket A, Ket B, Ket C, D. In the following way. So it's an operator operating on A. So it's alpha times A, where alpha is nothing but the eigenvalues. And So the question number 7 is, if observable O is measured in general, how many possible values could be measured, measurement could take? So we know that from the questions that there are 4 possible eigenvalues. That 4 possible eigenvalues are nothing but the 4 states if the operator operates on this wave function. So answer should be 4. So that is essentially D. So
Sorry, by the way, could you please share your screen?
All right. So just a moment. All right. So, okay. So question number 7 is like here. So there is an operator O, right? And it operates. So essentially it is kind of, let's say it's an operator and it operates on A, and it gives some alpha, and then the similar way is for operator operates on B, C, and we are getting alpha, beta, gamma, and delta, right? So what are the possible, what are the other possibilities? So possibilities are all these eigenvalues, corresponding eigenvalues, that is alpha, beta, gamma, and delta. These are the 4 states it could be. So question number 7 is that. So what we could, there is, wait a minute here. So I could write here, if that helps, like this operator A, similar is B, all right. So question number 7. Question number 8. Let's look at question number 8 now. So the question number 8 is this. Right, this is the question. Right, so there's a LaTeX code here. Sorry, I cannot. So all I can use is a text actually here, some text editor. And this is question number. So this is question number 8. So all the possibilities here, outcome of the measurement of observable states would should be. Let's look at another question here. This is the next question. Okay, so I'll stop. Yeah, so question number 8 is already answered. Which one? Yeah, so question number 8 also will be A, B, C, D pretty much. Yep. Any other question? So I can give you for question number 9. Let's go and take the hint. Upon measurement of here, this is question number 9. I will share again. All right. So question number 9 is upon measurement of this is LaTeX code. Let's remove it. And yeah. So hat O, that is operator actually, operator O. Okay, on function. So get psi actually. What is the probability that the value is alpha? All right. So what is the probability that the value is alpha? Essentially, so alpha comes from where? From here. What is? So, okay, on these operations, if you look at for alpha is actually, if you look at the beginning of these questions, the probabilities are given associated. All right. It's nothing but the values associated, the coefficient, the eigenvalues. So the question is from psi is equal to 1, essentially psi is equal to 1 by root 6. That is here alpha is 1 by root 6. Beta is 1 by root 3. And there is gamma is 0 and delta is 1 by root 2. So we know that probability is nothing but the eigenvalues of it's a square and modulus of the coefficient, so alpha. So what is A? For A, it will be 1 by root 6 square. So that is, it will be 1 by 6. So answer should be 1 by 6. So essentially, we know that function is here. Right? So it is nothing but psi is nothing but 1 by 6 times A, that is a square root, SQRT. This is also 1 by 3 SQRT under square root. And this is 1 by SQRT root 2. So the three states are there for the wave function. A here with alpha is 1 by root 6, beta is 1 by root 3, and gamma is 0. This is missing here. There is no, this particular state doesn't have gamma. And another is this. So essentially all these should, if we kind of look at the wave function, if we add up all these probabilities, actually essentially it should be 1. So let's check it if it is adding up to 1 by 6, then 1 by 3 plus 1 by 2. How come? Because 1 by root 6, square root 6 is squared is what? 1 by 6. 1 by root 3 squared is 1 by 3, and so on and so forth. And here I think it will come, and 1 by 6 plus 5 by 6 is equal to 1. So essentially it is. So what will be alpha values is nothing but 1 by 6. So for question number 9, it should be 1 by 6. Okay. And likewise, question number 10, you can do pretty much upon measurement of operator for psi, which is what is the probability that value beta is measured. So essentially operator, when you know that on a wave function, when an operator operates, the state gives is the same function, but with some eigenvalues. It is nothing but the eigenvalues are nothing but the state in which it will exist. Right, and so essentially the function times the value is nothing but the probability actually. So for beta, so question number 11, it is going to be for gamma. There is no gamma here. Okay, it is going to be 0. So for question number 11, so gamma is essentially 0. All right, because in the when the function is operating, actually the psi get is 1 by root 6. If you look at, then yeah, so essentially this is what the function is. This gamma is 0. Let me write it. So 0 times, because this function doesn't exist, so we can write like as if it was. Yeah. All right. For question number 12. So for question number 12, pretty much it will be same as from the equation. From the equation itself is given 1 by root 2. So 1 by root 2 square, that is 1 by 2. Likewise, for question number 10, you can look at, that is for beta. So beta is nothing but 1 by root 3. All right, let's look at some more questions. I will stop sharing because I'm not able to see what is coming in the chat box. All right, can we start from question number 1? All right, we will. And here someone has asked, Oswaldo, for 11, question number 11. Yes, I think for question number 11 is 0. Yes, absolutely. That's what's the gamma, because there's no gamma there missing. So essentially there is no state. Okay. Okay, what is 10 again? So 10, I think I answered it, 1 by root 3, and square it, so 1 by 3. Answer would be the last one. So for question number 10, again, we answered, right? So you just try to look at what are the conditions given for the questions preceding in 9 to 14. The wave function is defined as 1 by root 6 ket A plus 1 by root 3 ket B plus 1 by root 2 times ket D. Okay, so ket C is missing here, right? And so it doesn't have the probability value. Essentially, that state doesn't exist. So, and in that way, for question number B, is beta is 1 by root 3 square. So that will be answer will be the last one, that is D, 1 by 3. Okay, so we will go back, and as that is better that I should start from question number 1 itself. So since I am pretty much sharing answer, I could share my screen itself, right? That makes sense. We are not giving hint here because we are pretty much sharing answer. All right, so actually this is the first time I'm taking this co-hosting it, so I'm not sure, but perhaps I think you should be able to know it. Let's share it. Okay, so question number 1. The first postulate is establish how quantum states can be represented mathematically. Okay, so the second, a quantum states can be represented as ket psi in a Hilbert space. So you know why the first won't be a quantum states can be represented as a number on the number line. Well, it is not a number in the number line. It is an Argand plane. In fact, is so you know a standard is a complex number. This can't be a number line, right? Complex number is always represented by alpha times j times beta, or some x plus j times y, where x is x-axis, or let's say if you're putting in Argand plane, where so and j represents the imaginary axis, right, or some representative. So it is a kind of a point in the plane, or even so it can't be a one line. Okay, answer is second, of course, a Hilbert space. You know the Hilbert space is it is a kind of a vector space which has got certain properties it holds, and perhaps yeah, and a quantum states can be represented as a spherical surface. Well, it is geometrical representation of a in a Bloch sphere. Okay, but not the state. So we are looking for the mathematically, not geometrically. If geometrically, then third answer would have been correct. And a quantum states psi can be represented as a two-dimensional vector space. So two-dimensional vector space, no. So two-dimensional vector space is a kind of a fix. It's kind of confusing, this fourth one, but it is not the mathematical representation again. So it is essentially, it is showing that it is pretty much looks like the second and fourth are pretty much similar kind of answer. So had that been a kind of geometric here representation, not mathematical, then fourth or third could have been a strong contender for this answer. But for mathematically, of course, this is what mathematically is. Okay. Okay. So question number 2. Question number 2 is the second postulate of quantum mechanics establishes the observable quantities are represented in quantum mechanics in quantum. Okay, that's okay. So many quantum mechanics here. All observable quantities are what? So you know this is coming from one of the quantum mechanics postulate, right? There are so pretty much this is a Hermitian operator. You know that the Hermitian operator is what? As again, it's a Hermitian operator is an operator is you can represent as a matrix where it's a transpose and conjugate transpose is the same. So let's say you take a matrix and perhaps you have you know that. If it is confusing, just remember from the postulate itself, the second postulate. All right. So, well, we can kind of look for the postulate. Just a moment. Let me search that and come back to you. See the questions, if there is any other questions here. All right, so someone has asked the eigenvalues or alpha, beta, gamma, delta for question number 7. Okay, yes, someone has commented, that's fine. Okay, so Jamie has asked question number 13 and 14. All right. Okay, I think we did cover it, but let me revisit that question again. So essentially, we are kind of going every question from 1 to 14 questions are there. So we are going one by one. But let me jump directly to 13 and 14 as well, because someone has asked specifically. And when there is no questions, we will kind of traverse back again from wherever we left it. All right, so question number 13, if we perform a measurement of operator on psi, get psi, that is a function, and the value we obtain for the measurement is delta. Okay, which of the following gives the state of the psi after this measurement? Okay, so essentially the psi, if you're getting delta pretty much, so which state, eigenstates it corresponds to? It corresponds to D, right? Okay, so that is pretty much the answer, because any wave function is after an operator, like even Hermitian is also an operator. Let's say this is, we don't know whether it is a Hermitian operator or not, but let's say this is an some kind of Hamiltonian or some kind of operator O here. It operates on the function. The function will give you eigenvalue times the function itself. And that function itself is nothing but it's one of the state, right? And one of the state is called D. So the D will be associated with the eigenvalues. So D is nothing but the eigenstate of that function. And corresponding eigenvalue is delta. So the answer should be delta here. So since it is given the measurement is found to be delta when the wave function collapse, which state it has been after the measurement, because after measurement we disturb the wave function. So it was in a state D. All right, so KD would be the answer, the fourth one. All right, question number 14. Let me share again. All right. So question number 14 here. We did answer question number 13 and we explained why, because delta is, sorry, you just kind of need to refer from here. From previous year, right? This is where you need to refer here. So consider an experiment which measures observable different states, its position, momentum, whatever could be the states. And whenever operator operates on this function, it gives 4 eigenvalues, alpha, beta, gamma, and the corresponding eigenstates are A, B, C, D, right? So when we are looking at if the measure state value is delta, it will correspond to D, because this is what the operator says. All right. Had that been something else, it could have been changed. It will be accordingly. The answer would be. So, and one thing also to note here is like all these states are orthogonal. So essentially, it can be a 4-dimensional space where every state is perpendicular to each other. So only one state it can be, not other state at any point of time, right? But not all states can be, if we look at. So here, so for 14 number question, again, the value of we obtain of the measurement. So measured value is alpha. So essentially the eigenvalue is alpha. So eigenstate would be which one? This one. So psi was essentially A, the eigenstate. So the function was there. Because so this is pretty straightforward. It's not that complex. If you look at all those the 5-6 postulates from quantum mechanics and what has been shared, we just need to look at, read it, whatever the conditions are, and why we can pretty much revisit, and pretty much answer lies here for question number 9 to 14 here. Look at here. All right. Okay, so we will go back and let me see if there are any more questions here. Sharing. Cannot see the chat box. Somehow I need to stop here and then again see that window. Okay. Question number 4. Okay, can you explain the fourth postulate? Okay, so the fourth postulate, let's look at the question. The fourth postulate of quantum mechanics tells us the probability of measuring a given value of an operator, the A hat. The postulate states that the probability of measure a state psi, okay, wave function in eigenstate A operator is alpha 1 is obtained by. So okay, so this is kind of the it is from the inner product of psi and A1. So okay, so let me bring that postulate for you. Postulates of, so there are kind of 6 postulates, and 4 is the average value of observable corresponding to operator A is given by. So essentially it is coming from a weighted average actually. So you know that there is a okay, let me share this first. All right, I hope you are able to see this postulates of quantum mechanics here. Okay, there are 6 postulates. So we are talking about the fourth postulate, right? The average value of observable corresponding to operator A is given by this, right? So you know that this, what is this notation? A to A is kind of a dot, inner dot product here, and it is nothing but a wave function with the dot product, and then it's integral over, it's a weighted integral by divided by the function itself, which is at dot product. So it's kind of weighted, it has been weighted by with the operator itself. So that's what so mathematically it is pretty much explaining it. So let's say, what is the weighted average? So let's say if there are kind of n different states, it has the first state is alpha, right? So let's say the example was for question number 9 and 14, 9 to 14, right? So if we put that question here, so we know that there is only 4 states. It's a discrete, essentially actually continuous, but let's say it is alpha times A beta times B plus gamma times C plus delta times D divided by A plus B plus C plus D. So that would be the answer. But here, this is generic formula. So we don't know the function, but essentially it can exist from -infinity to infinity. So we are taking integral, it is continuous. So that's how it is taken. It is nothing but a kind of taking an average and weighted average, because we are kind of weighing it for their corresponding state. So had that been alpha times A, if it is kind of, we know that there are only 4 states, then alpha times A, then plus beta times B, gamma times C, delta times D divided by A plus B plus C plus D. A similar way. So this example is kind of a continuous. All right. So hope that explains. Let me look at the chat here. Hope. Okay, so I try to answer Jamie question here. After that, yeah, we have Lawrence asked to start from question number 1. Okay, yeah, we have been doing it. We will go back again, whatever we have. Okay, question number 3. Answer is D. I think, yeah, I need to check it. Yeah, the measurement in quantum mechanics are probabilistic, yes. The third postulates of quantum mechanics establishes what values are possible for measurement for a given observable. So upon measuring an observable represented by operator A, the possible outcome of the measurements are given by, so yeah, so essentially all the eigenvalues of A. Yep, that's the correct. All right, so 4 is also answered. Now we will go to question number 5. Okay, let me say it again. All right, so question number 4 is also done. Question number 5. The fifth postulate of quantum mechanics establishes how measurement affect a quantum state. After measurement of an observable state A, so we know that after any wave function, and that's how the Heisenberg uncertainty principles comes in, like we disturb that state, and that's how there will be uncertainties, and in the measuring either state or its velocity, momentum, whatever is related to or its position. So here, and if we kind of measure it, it collapses. The state collapses to an eigenvalue, and that is where the eigenvalue at that eigenstate, and the probability with which it collapses to that, how many times. Let's say we are kind of trying to observe it, and observing nothing but kind of a operator and any wave function. So maybe, so it is probabilistic. You know that it is all probabilistic. So it might happen that alpha times, there are 4 states. Let's say the wave function collapses to 4 states, which is, let's say, take an example. Okay, so 4 states like alpha, beta, gamma, and delta is the 4 states with the alpha they are kind of going into after observation. And so what will happen is, if we kind of measure it, and if it is going into gamma state, the probability, the gamma will be a value, actually it is, and the gamma, it's going to a state C, the gamma is the value, and the gamma is the probability, is the gamma square, actually. So here we saw it in the example 1 by root 2, or gamma was 0. For beta it was 1 by square root 3, for alpha 1 by square root 6, one of the example for question number 9, 14 and ahead. This is the kind of that particular eigenstates. So how many times? Let's say you are observing it for 100 times or 1,000 times. So let's say gamma value is something like 1 by 6. So it means out of say, let's say you're measuring for 600 times. So roughly 1 by 6. 600 times of by 6, like almost 100 times it will collapse to that state. We don't know which state it will go, whether it can go to A, it can go to B, it can go to C, it can go to D, right? But what is the probability it will go? That's how it is tells. If you multiply by the probability with the number of events, pretty much it will give you a rough estimate that out of, let's say, 600 times you are measuring it. For the sake of brevity, I use 600. You can have any number. So essentially, it is going be going in that state almost 100 times. All right. If let's say value for alpha is 1/2, it means in state A, it may be going almost 300 times out of 600 times you do the experiment. Okay, so this is the probabilistic measure actually. And later on, what we will learn how to kind of estimate those probabilities so that the wave function is constructed, and there will be always some error actually. All right, okay. I think I should not digress from here. Let's look at question number 6. Okay, so question number 6 is the sixth postulate of quantum mechanics states how quantum state changes in time. The evolution of quantum state in time is so determined by the action of unitary operator that preserves the normalization of the state actually. Yep, this is coming from the postulate here. We did look at, perhaps I think you are able to see this. Yeah, so the total wave function must be antisymmetric with respect to interchange of all coordinates of one fermion with those with another. Electron spin must be included in set of coordinates. Pauli exclusion principle is a direct result of the antisymmetric principle. Okay, so yeah. All right, so here. And question number 7, I think, yeah, from pretty much we have answered from here, I think, yep. So let's stop here, and I think pretty much we are done with the questions. If you are able to, okay. Okay, all right, the question is full through. All right, okay. Here, not everyone knows calculus. Will it be any way to explain that postulate for in a different way? All right, I think I did try to give an average, weighted average it is called. Like in calculus, of course, we know that is a continuous function, so we integrate it. But I try to give an example of alpha times A, beta times B, gamma times C, and delta times D divided by. So let's say, okay, let me give another try. Let's say if we have a function and it can occur, the occurrences, let's say some probability or how to give an example. Yeah, so let's say that we measure something weighted average. To give an example, what is the best? Okay, let's take a class example here. So let's say a student and we are trying to measure the student BMI. Okay, so how do we measure? And we want to calculate average. So is that way like we can kind of calculate it like everybody's weight and divided by everybody's height? I don't think it is a good metric to do that. What we do, we calculate everybody's weight multiplied by that person's height, because essentially we are calculating something weighted average. Then so weight times height of first student times weight W2 times height of the second student, and divided by, we are measuring that weight. So essentially what is the average weight divided by height. Or if you want to measure it average height, then we have to divide by that only weight. So W1 H1 plus W2 H2 divided by H1 H2 H3 all up to Hn, whatever the n number of students are there. What you will get, you will end up, because height and height cancels, essentially the metric actually, not directly, and the measured quantity of that will essentially be left will be weight times height divided by height, and what will be left over is weight actually. 30-minute. So whatever is the value, we need to kind of multiply it by scale it. And that's how the weighted average comes into. Like we are giving the weight as per the quantity. So essentially, the fourth postulate is nothing but it is kind of weighted average. And how do we get the weighted averages? Kind of we do the dot product, because essentially all these functions are a vector quantity, and we take a dot product, then it becomes a scalar, that is becomes a number. And dot product is nothing but the inner product, which is called, so mathematically. So that is what I try to kind of explain. Hopefully you try to understand it. If not, maybe we will try to kind of convey this to our in the lab, and maybe TA could help here in a better way. All right, so okay, Yara is asking for, I missed the explanation for question number 2. For number 2, question number 2. All right, I believe question number 2. So, all right, okay, good. All right, okay, so I think we have pretty much. Yeah. So we have few minutes left over here, and pretty much we are done with. But if there is still those questions, out of those questions is still something, I'll be happy to explain, no problem. All right. So I wish I could have something to write, and I guess someone is waiting here. Okay. So I wish I could have something to kind of write and illustrate it, but unfortunately I don't have. And then so when I could scribble and it could have a free-flowing text, it could have been easy to explain or draw some diagram or pictures, but unfortunately I don't have any such that aid with me. So bear with me. I believe one thing I should, meanwhile, if there is no questions coming up, but since we have a few minutes left, 5-6 minutes, I will try to explain what is operator is, because all these questions are related to operator. Anyone have confusion about the operator? Indeed, when I read it, of course, I have that confusion. What is this operator? Why this is operating like that? Why these states comes and all this? So it is a little bit of mathematical, but there is a kind of explanation to it. So it's like, so imagine there is a wave, okay? So let's say sine wave, okay? And so sine wave is a kind of continuous wave, right? So let's say a system is there which is kind of churning out always the sine wave, sinusoidal wave. And at any point of time, what you do is kind of take a measure, a snapshot, a picture. So that truss and that trough and crest will come, and that is right. That any part of it will come. One time it may be that you take like there is a one complete cycle, somewhere it is just half of the cycle, but the nature of the wave remains same, right? It is based on that how much you are taking the picture, how much you are measuring it. So think of that. These operators are nothing but actually it is giving the same function. It is operating and it is churning out the same function. So operator is nothing but it's a kind of a function or a kind of where it gives you the same function, same output. But if the output is not complete or a part of it, it is there we can say that it is the one of the state, and that state is nothing but the kind of eigen states. And with the probability of that state happening is eigenvalue. So all these questions are related, whatever, almost all except those postulates, and those out of those as well, 2, 3, 4 questions were there. So these are nothing but related to operator. And essentially in quantum mechanics, that is what I think we have learned, and perhaps Amir and our TA will pretty much explain those each time, because this is nothing but the operators actually, and mainly it is Hamiltonian operators or something which we will learn perhaps in later point of time. Yeah, so this is all. Okay, so question number 5. Someone asked question number 5. All right, let me repeat it. Question number 5. Question number 5. Wait a minute. I think by mistake I close it. Canvas, I need to open. Some question number. Yes, so question number 5. Okay, so let me look at what the question person asked. Yes, the question number 5 answer is B. The question is actually the 5th postulates of quantum mechanics establishes how measurement affects a quantum state. And after measurement of an observable state A, so it will collapse to that eigenstate of that observable operator. So yep. If it is observable state was A, then it must have collapsed to that eigenstate actually. So it's like was given example, like a wave function which is kind of a sinusoidal wave, let's say, just for sake of convenience, and let's say a wave is coming and then you kind of chopping it with a 2 scissor. A wave is kind of coming out, and then let's say on a cord, and let's say preserve the shape at the time you kind of chop it, a fraction of it. So it depends on where you are cutting it, that part, and what shape it has. The shape is going to be sinusoidal, right? But at the same time, what is that state is whether it has got up or down, or where it is, the amplitudes is. So that is where it we can kind of relate it to the different eigenstates. And let's say only 4 states are which you are able to kind of capture. So those are the 4 states. And so if you kind of measure it, if you do experiment, you are able to measure all your states, which will kind of add up to let's say 1,000 experiments you did, or essentially not thousands, usually law of large number holds here in any kind of probability theory. So statistically, it will be millions of something of that range when it is measured. But in a lab environment, I'm not sure how it is measured. Maybe Akshay would be the right person to, because he measures all these things. Perhaps he will be able to answer. But that's how it will be. Something like it will be number of states which is observed when it collapses and measured in a particular state, which is also corresponds to, that is its eigenvalues. And that eigenvalues is nothing but a number of times or the related probability when that particular state is observed out of entire experiment. All right, so this is all. I think we are at the top of the hour.
Yep, that's 5 o'clock. Thank you so much, Amant, and thank you everyone for joining us today.
Yeah, my pleasure. Thanks. Bye-bye.
Thank you, everyone. Have a great rest of your Friday.